Hello, and welcome back to the Taurus Report, where we are going to chronicle the adventures of a bull in the China shop of cosmology. And in this episode, we're going to take a look at Oumuamua. For those of you who might have forgotten or not known about Oumuamua, it was the first interstellar asteroid, like an asteroid that came from some other solar system outside of our solar system and came speeding through our solar system. And the thing that was interesting about it is when it passed the sun, it did not appear to follow the dictates of the standard gravitational force. There was a little bit of a difference there, and this caused quite a commotion. So we are going to discuss that. And interestingly, as we proceed through the next few episodes, we will see that far from being anomalous, this behavior of Oumuamua actually has bearing on everything we've been talking about, specifically on the idea that we need to modify the standard theory of gravity in cosmology. Before we begin and get to Oumuamua, I would like to just remind everyone how to get to our website here. So if you type in Taurus Report, all as one word, .com, then that will bring you to our website. Now, from our website, you can get to the YouTube playlist of all of our episodes. You can listen on Spotify. And also I have a Facebook page. And the Facebook page is a new explanation for dark matter and dark energy. And lots of different articles and the videos are posted there and so forth. Also, the paper, if you want to get a sort of spoiler of where all this is going, this is a formal paper that is under submission right now, but this is the preprint. If you click on it, you get the preprint. And in this paper, I explain very carefully a new way to look at the gravitational force, and I explain how this is, how the gravitational force is generated and why. And it is just using an understanding of particle physics with no mysterious energies like dark energy or mysterious forms of matter like dark matter, or any kind of forces or particles like that. Everything within the theory uses well-known forces and particles that are known in particle physics today. So if you want sort of a spoiler or preview of where all this is going, and I am going to go over all of it step by step to explain how all this relates to the Webb telescope results, because all of it comes back to that. Okay, we are seeing a version of cosmology with the Webb telescope where, in my opinion, standard theory just cannot explain what we're seeing. Now, this article that I've written here was submitted in March of 2022, way before any of the Webb results came out. And the gravity as described in this article is perfectly consistent with what we're seeing. Now, the title of the paper is Chasing Oumuamua, an apology for a cyclic gravity in cosmology, consistent with an adaptation of general relativity. Later in the paper, I sort of go in depth and explain how general relativity would have to be adapted to be consistent with all of this. And the paper starts with Oumuamua. and how Oumuamua challenged standard gravitational theory. At least it challenges it, in my opinion. And I will explain that as we go on here. I'm going to speak a little bit about Oumuamua. Oumuamua came through the solar system in 2017. It was discovered by Robert Warwick using the Haleakala Observatory in Hawaii. And I'd like to just show an animation. This is the Wikipedia article on it. And I will include this link, like all links that I reference. They will be included in the comments. Looking at this picture, this shows kind of the path of Oumuamua. It passed through, coming inside of Mercury's orbit. So it's coming from up above here. It passed inside of Mercury's orbit and then out of the solar system. And here I think we have a little animation of it. Okay. And so what was the big deal about that? I am going to show that by doing a few drawings here and explaining a few things about that. What was so strange about Oumuamua? Let's suppose this is the sun. When Oumuamua passed near the sun, it made like a path, let's say like this, okay? And the thing is that astrophysicists have the prediction of the behavior of things like asteroids, comets, and so on and so forth, down to a pretty exact science. And they were expecting the path to be something like this, let's say. And so Oumuamua behaved as if gravity was not pulling on it in the normal way. Now, the interesting thing is, in an orbit or a flyby like this, the path is not so much dependent upon the small object. You have a gravitational attraction between the sun and Oumuamua, but because the sun is many orders of magnitude more massive, the path that it follows really isn't dependent on, what the mass of Oumuamua was. So this path should not deviate no matter what the mass of Oumuamua was, and it just did not follow the expected path. And so the question immediately comes to mind, at least to me, the question came to mind is it a coincidence that the first interstellar visitor we have ever in history to be observed, I presume there were others that were not observed, but this is the first one that was observed, also behaves in a gravitationally, strange way? Is that a coincidence? If it is not a coincidence, then it would mean that perhaps objects in other solar systems might follow a different gravitational law. And that would be exceedingly strange because we have distant observations from all over the universe, and it seems like gravity behaves the same most of the time. However, we have intriguing anomalies every once in a while, and Oumuamua is one of them. Let me just show an artist's picture of it. This is an artist's representation of Oumuamua. It was presumed to be elongated because of the way it was reflecting light, and it was presumed to be spinning. So the question is, are there any other examples of anomalous acceleration in our solar system? After doing research, I found that there are actually quite a few. So it seems as though gravity behaves predictively most of the time, but there are some anomalous occurrences. One of the most interesting to me is comets, and I would like to speak a little bit about that because I think that what is going on with Oumuamua is related to what is going on with comets. Now, Oumuamua did not have off-gassing. Comets, when they're traveling near the sun, we see this tremendous amount of off-gassing from them. And astronomers for a long time have presumed that the anomalous accelerations that we see with comets, that must be caused by off-gassing. So because the comet, when it gets close to the sun, starts giving off all this gas, then the idea is that that gas makes the comet move in a way that is not explainable just with the operation of gravity. And so it is called non-gravitational acceleration. Now, if Oumuamua had come close to the sun and exhibited some kind of off-gassing like that, then for astronomers there would not have been any mystery. They would say, "Oh, well, it's behaving like a comet, right? It's throwing off gas, and the gas is causing a strange sort of motion, and so we assume that that would be what is going on." Now, in Oumuamua's case, they did not observe any kind of off-gassing at all, and so it was hard to explain this by appealing to the behavior of comets. Now, later on, in later episodes, I am going to have an episode specifically about other anomalies in the solar system, including comets. The behavior of the asteroid Bennu is another one. The flyby anomaly is another one. The Pioneer anomaly, which some theorists have claimed to come up with an alternative explanation for that, and I think they're mistaken. But in any case, my point is there are a lot of different gravitational anomalies here within the solar system, and I am going to make a clear case that those anomalies are actually very much connected to the mysteries involving dark matter and dark energy. That all of these gravitational anomalies can actually be explained with an elegant and simplified theory of gravity. For now, as I go forward and I diagram out this behavior of gravity, I'm going to compare it to Newtonian or general relativity for a lot of these anomalies we're going to be discussing, because we're talking about non-relativistic speeds. Newtonian or general relativity will kind of give the same results. And so I'm going to diagram out the way that I think gravity varies. And for now, I'm going to do that without explanation, meaning I'm not going to justify it or explain why gravity behaves that way. And so for now, I'm just going to describe it, but hold out the possibility that as we go on in the next several episodes, I will then supply an explanation of why gravity behaves that way and why it takes that form. But for now, I'm just going to describe that form. So now we will go once again to torusreport.com. Torus Report, all one word, .com, to bring us to the website, and we are going to go to the link to the paper on cyclic gravity and cosmology, CGC. And we will pull that up. And I want to scroll down to skip some of this stuff right in here, and I'll be going over this later. I explained the basis of why gravity behaves that way. And I'm going to skip that for now. And I want to scroll down to this diagram showing the gravitational force in our solar system. this diagram right here. So let's zoom in on that a little bit. And this is in the paper. Now, this purple line right here, you can think of it as showing the gravitational force as you go far away from the sun. Now, the green dots are the planets. This one here, by the way, is Oumuamua. This is Mercury. This is Venus, the Earth, Mars, and this is actually Ceres. It's not Jupiter. And so the purple line represents the gravitational force according to Newton or Einstein at that distance. And we can see how perfectly, almost perfectly, it predicts the gravitational force where the planets are. Okay? And notice how it's very smooth and nice and doesn't deviate. And what I am claiming is that the gravitational force under certain circumstances, which again I will explain in time, varies sort of as a wave function. Now it is true that it decreases with distance, but it's not always perfectly predictable. Now I have to be clear here that I am not claiming that gravitational force in our solar system follows this blue line. Okay. What I am saying is that the gravitational force under certain circumstances can vary like this, and these variations here, they're kind of exaggerated for effect. Okay. In reality, the variations would be super tiny. And Oumuamua is a special case, which I will get into. So you'd need a very large variation to explain the motion of Oumuamua. But what I am saying is that under certain circumstances, gravity can vary like this. And I am claiming that we have evidence of this right here in our solar system very often. And that evidence is misinterpreted by current theory. So notice that it is possible when you get variation like this, sometimes, and we will also get into this later, sometimes gravity can actually be repulsive instead of attractive. And that will become a big factor when we start talking about cosmological expansion. If gravity varies in the way that I'm describing, then it would make perfect sense, for example, if, let's say, this is the sun. So you have the sun at the center of the solar system, and the planets are orbiting in very roughly circular orbits like this. Not exact circles, but roughly circular orbits. It would make sense that if the planets maintain their approximate distance from the sun, then they would not experience, any of these differences in gravitational force that I'm talking about. Whereas if you have an object traveling radially, and when we use the word radially, we mean traveling like sort of directly in like this, okay, where you have some sort of radial velocity instead of an orbital velocity. And that is the case with something like a comet. If a comet has an orbit like this that is very eccentric, then you may think of this as being sort of like radial velocity here. And if gravity varies in the way that I am talking about, then what you would end up with is the comet would experience periodic anomalous accelerations. In other words, sometimes it would seem as if it is being pulled by the sun less than expected. Other times it would seem as if it is pulled by the sun more than expected. Other times it's going about what we'd expect. And so comets, an object, if gravity varies in the way that I am talking about, if I'm right about this, then comets would experience this sort of variation in acceleration, whether or not they were off-gassing. And this entire concept, it brings me to one of the ways in which the theory I'm proposing, CGC, can be confirmed or falsified. Because I am claiming that if an object travels at high radial velocity in our solar system, it is going to experience anomalous accelerations. Now, and those will be periodic. Like you might get, as it's traveling, you might get more than expected attraction to the sun, less than expected, more than expected, less than expected, like that. Now, traditionally, astronomers have explained the behavior of comets like that by saying that the comet is off-gassing and maybe the comet is rotating as it's traveling, and so the direction of the off-gassing will cause its anomalous accelerations to be periodic. So as it rotates, you get the same pattern of acceleration, deceleration because of the rotation, and the off-gassing is directional. Now, I argue against that in the sense that I think that if a comet is off-gassing, I suspect that they off-gas in all directions approximately equal. I suspect that that's the case. And so I don't think that you would observe from off-gassing this acceleration that astronomers have been attributing to it. Also, I will make the following claim that is testable. I would say that any object traveling at high radial velocity, including an asteroid that was rocky, not icy, and not off-gassing at all, this asteroid would experience that same pattern of accelerations and decelerations. And the only reason that astronomers have not observed that is that, there's two reasons. First, the things that come on these wild, highly elliptical orbits from the outer solar system, those objects tend to be icy objects, and so they all off-gas. So we haven't really had rocky items that are very, very easily observed. And that's what brings me to the other problem, is that a comet is very easy to observe because of this off-gassing, right? It's easy to find in the sky. It's easy to observe it as it travels. And so for both of those reasons, the fact that most of these types of objects on a very elliptical orbit are icy, and for the fact that they're just simply easier to observe, I think that astronomers haven't really observed so much objects traveling at high radial velocity that are not icy and not off-gassing. In order to confirm what I'm saying, that you're going to get those same sorts of deviation from expected acceleration. Now, we have an excellent example of that was observed, and that is Oumuamua. Okay, Oumuamua came in at high velocity, a high radial velocity, and we did indeed observe unexpected acceleration. And I think that CGC explains why we saw that. Now, I do want to mention, this acceleration was so unusual that I mention a author in my paper here at the very beginning, Dr. Loeb over at Harvard, and I have to say I agree with his reasoning entirely. Okay, Avi Loeb, he came to me, which is an inescapably logical conclusion, that what he was saying was that. Let me get back to my video here. So what Avi Loeb was saying was that, okay, if we assume our theory of gravity is correct, and we see no off-gassing that can be causing this, then this object must be under some sort of artificial propulsion. And so Avi Loeb was saying that it must be an alien spacecraft. And to me, and in some circles he was sort of ridiculed about this, but to me, the logic is inescapable. If you can't find any kind of off-gassing or some kind of propellant, if you can't find that, And if your theory of gravity is correct, and an object moves in an unpredictable way like that, then artificial origin is, to me, the logical conclusion. So what he was saying made a lot of sense to me. Now, of course, I disagree with it because I believe that our theory of gravity is not correct. And in the coming episodes, we will explore more and more of that, where rather than simply describing it, I will begin justifying why gravity behaves in the way that I claim it does. So thank you once again for watching. In our next episode, what we are going to start doing is getting into the mechanics here of explaining why gravity behaves in this way. Why does it vary? Why can it be sometimes repulsive? And so on and so forth. I'll kind of go step by step through all this. And then, of course, as we near the conclusion of the paper, I will bring it all back to what we are seeing in the Webb telescope and why this is all, why CGC is consistent with that and why it all makes sense. So again, thank you very much for watching, and I hope to see you next week. I usually upload the videos either Saturday or Sunday, so sometime around then is when I will be uploading the next episode. Bye-bye for now.